Awesome. Our next presentation is by Jeffrey Cummings from Indiana University, and he'll be telling us about carbon star formation as seen through the non-monotonic initial final mass relationship.
Yes, good morning, everyone. I'd like to thank the committee for giving me the opportunity to talk about our recently published paper with the same title as my slides here conveniently. But let's jump right into it. So the initial final mass relation is simply a direct comparison of a star's initial mass to its final mass after it goes through all of its stages of evolution to reach a white dwarf. So here we show our most current initial final mass relation stretching from initial masses of 0.85 solar masses all the way to roughly 7.5 solar masses, looking at 94 individually observed white dwarfs from across 17 star clusters, to where we really need to look at white dwarfs and star clusters because this provides the critical information that we need to infer what their initial characteristics were. But how do we derive such a relation? So most white dwarfs are going to be DA white dwarfs with pure hydrogen atmospheres producing very strong and clean Balmer features. And so doing spectra of these white dwarfs at low resolution but high signal noise, most critically at Keck LRIS, which really provides the necessary characteristics to observe such targets, which is why we've observed 51 of these 94 white dwarfs at Keck LRIS alone. But fitting these Balmer features using the most recent models of Tremblay et al. Allows us to derive information about their current temperature, their current surface gravities, and infer their masses, their cooling ages, their luminosities, and their colors. In comparison of these spectroscopic characteristics to their observed photometric characteristics relative to these star clusters allows us to really do thorough membership tests because we really want these white dwarfs to be members of these star clusters. And then once we have this membership, we really look at the detailed characteristics of these star clusters themselves. For example, here's NGC 2516, and measuring their parameters, most critically their total age, allows us to do this final step of simply looking at cluster age minus cooling age of this white dwarf, resulting in the evolutionary timescale of this white dwarf's progenitor to the AGB, and hence their initial mass, producing again this relation that we see here, which shows a lot of interesting trends, some changes in slope, and also some interesting regions with broad intrinsic scatter. In comparison to recent evolutionary models like the MISS model from Choi et al. Really allows us to dig deep into some of the limitations and challenges that current evolutionary models are still having. Like, for example, in the higher and intermediate masses, above 3 solar masses, we're finding that many of the current models are lacking in how they're handling convective core overshoot and how they're introducing effects of rotation, to where variations in rotation will actually produce spreads in the intrinsic final mass relation. And so faster rotators will fall up here, while slower rotators will produce white dwarfs along the lower envelope. So that's now focused though on the lower left region, the low mass region of this initial final mass relation. And here we find that rotational mixing and convective core overshoot really plays no significant role here. And we can look at these 6 groups of white dwarfs taken from these 6 star clusters and confirm this by looking at intercluster scatter, showing there's no meaningful scatter of these individual white dwarfs. It's all can be explained quite well by just their simple observed errors. This also allows us to do more detailed fitting of the trends here. So if we just throw in a simple linear fit across all these low mass white dwarfs, it really seems to be lacking. And we could also, based on this initial final mass relation, create a synthetic population of galactic white dwarfs. And we see that the mass distribution of the synthetic population doesn't match very well with the observed population of white dwarf mass distributions. It's close, but it's not great. And also just this simple fit really seems to be lacking. So we could start looking at more complex fits, like these different fits based on different mechanisms, different processes within these lower mass regions. But we don't have time to get into all the reduced chi-squareds and goodness of fit tests that we were doing. But we really show that in this lower region right here, you really see significant evidence for a kink type of shape shown here in black. But then what do we do in this region? We're a bit lacking in our initial final mass relation data, but one might just say, oh, let's put a nice plateau here. But this really doesn't match very well with population synthesis, because this would significantly overproduce 0.7 solar mass white dwarfs. So we have proposed a kink. So this kink is sort of an unexpected type of shape, but it really matches well with the data and also produces a very consistent distribution of masses in our synthesis analysis. But how could such a shape be true? How could such a shape come out from stellar evolutionary models, carbon stars? So as third dredge up becomes deep enough during the thermally pulsing AGB phase, as you start to reach masses of roughly 1.5 initial solar masses at solar Z, you'll start dredging up significant amounts of carbon at the very final stage of these stars' evolution. And so this 1.5 solar masses is right where this kink starts to shoot up. And this dredges up a lot of significant carbon, but how does quickly changing carbon abundances and carbon over oxygen ratios affect the resulting evolution? So interestingly, many people tend to just ignore these abundances when looking at mass loss rates in AGB stars. So simple Blocker et al. Relations just produce pulsations and increasing mass loss rates. And while increasing carbon abundances are occurring, once you reach about a carbon of oxygen ratio of 1, the mass loss rates just still are continuing to shoot up, and you expel the entire shell of the AGB star. And then you expose the white dwarf. But interestingly, recent work looking at carbon-oxygen ratios and how these are critical drivers of dust production show that once you reach a carbon and oxygen ratio of 1, you're no longer able to simply produce dust, and your mass loss rates plummet. So introducing this effect into the evolution has the mass loss rates plummet once you reach this point, and so then you're no longer expelling off the outer shell, and you have additional time for evolution. And this produces also more carbon in the final stage, but most importantly, extends the AGB phase.
Time to wrap up.
What occurs during the AGB? Core mass evolution. So right in this particular region that we're seeing, to where carbon-oxygen ratios tend to hover around 1, the thermally pulsing AGB phase is extending, and this produces not only interesting carbon results, but much more massive white dwarfs. So this is critical in better understanding production of carbon in the galaxy, better understanding distributions of white dwarf masses, and third dredge up processes in AGB stars. Thank you.
Thank you. While we're waiting for people to type in their questions, I had a quick question about rotation. Yeah. You show that there is rotation scatter in all the different clusters, but do you see difference in the amount of rotation in different environments or in different clusters?
In general, we don't see much evidence for that, other than as you go to higher and higher masses, your variations in rotation rate will increase more and more. And then your sensitivity to rotation rates on the resulting evolution of the core also continues to increase, which is why when you looked at the highest masses, as you get to higher and higher initial masses, the scatter just appears to increase and increase. And we showed quite thoroughly that simple observational errors were not at all able to explain this scatter. But some of the more recent rotational models do quite well explain the scatter here. But the region where we're looking at carbon stars is just this little edge down here, and rotation does not seem to be driving much issues there. Again, it's more related to mass loss rates and dredge up.
Thank you. Let's see, we are out of time. And again, we can continue the questions on Slack.